Our universe may not have a single creation story. We are about to explore 25 of the most fiercely debated theories concerning the origin of everything. You will discover ideas that question the very nature of reality, from a start in fire and density to concepts where time itself is an illusion. What if the Big Bang was not the true beginning? What if our cosmos is just one page in an infinite book? By the end, you will possess a sweeping view of cosmology's greatest frontier, the ultimate question of where we came from. Which of these controversial origins feels the most plausible to you? A singular moment of infinite density marks the starting point of our cosmic story. This is the Big Bang Theory, the prevailing narrative of our universe's birth from an unimaginably hot and dense state nearly 13.8 billion years ago. From that initial fireball, space itself expanded, cooling over eons to form the first particles, then atoms, and eventually the stars and galaxies we see today. It is a story supported by a wealth of evidence, from the observed redshift of distant galaxies to the faint afterglow of that primordial heat, the cosmic microwave background radiation that fills all of space. Yet for all its successes, this foundational theory is built upon a profound mystery. The equations of physics break down at that very first instant, the moment of the initial singularity. What does it even mean for the entire cosmos to be compressed into an infinitely dense point? What set this entire chain of events into motion? The theory describes the aftermath of creation with remarkable precision, but it remains silent on the ultimate cause. It cannot tell us what, if anything, came before that moment. Was there a before, or is that a question as meaningless as asking what is north of the North Pole? The controversy lies not in the expansion we observe, but in the enigmatic trigger and the unsettling nature of a beginning that defies our very understanding of physics. But the human mind recoils from the idea of an absolute beginning. A rival theory emerged, offering a profoundly different vision of an eternal, unchanging cosmos. The steady-state theory proposed a universe with no definitive start and no impending end. In this elegant model, the cosmos is infinite in both space and time. It does expand, yes, but as galaxies drift apart, new matter spontaneously and continuously forms in the voids between them. This delicate, constant creation of just a few atoms per cubic mile every century would be enough to maintain a perfect cosmic balance. The overall density of the universe remains constant, presenting a forever universe that has always looked on the large scale essentially the same. It was a beautiful and philosophically comforting idea, a cosmos that never needed a genesis event, yet this elegant challenger met its match in a faint, persistent hiss. The discovery of the cosmic microwave background radiation was a death knell for the steady-state model. That all-pervasive glow is not the signature of a steady state, but the cooled remnant of a primeval fireball, the echo of a hot, dense past that the Big Bang Theory so perfectly predicts. The universe, it turned out, was not eternally the same. It had a dramatic history, a story that began in a state of unimaginable heat. Yet the echo of that primordial fireball does not necessarily mean our universe had a single, unique birth. Another profound idea suggests that the Big Bang was not the ultimate beginning, but merely a violent transition in an endless cosmic rhythm. This is the Cyclic Model, a vision of a universe that breathes. In this theory, our expanding cosmos is just one phase in an eternal cycle. Eventually, the outward rush of galaxies will slow, halt, and reverse. Under the relentless pull of gravity, every star, every planet, and every atom would be drawn back together in a cataclysmic reversal of the Big Bang, an event cosmologists call the Big Crunch. The entire universe would collapse back into a state of immense heat and density. But here is where the cycle renews itself. Instead of ending in a final singularity, that ultra-dense state could trigger a rebound, a new Big Bang that launches another expanding universe from the ashes of the old one. The mechanism for this rebirth is a matter of intense debate, often involving speculative physics where new fields of energy drive the cosmic bounce. The appeal is undeniable, a cosmos without a true beginning or end, an infinite series of worlds being born, dying, and being reborn. But does the evidence support such a poetic vision? The fate of our universe hinges on a critical unknown, the overall density of matter and energy. Current observations suggest the expansion is actually accelerating, driven by a mysterious dark energy, making a future big crunch seem less and less likely. This does not completely rule out the cyclic idea, but it forces its proponents to imagine far more complex and exotic mechanisms for the great turnaround. The debate continues, a fundamental clash between a universe with a definitive start and one that has simply always been, forever renewing itself in an unimaginably vast dance of creation and destruction. But what if the Big Bang was not a unique event, but merely a local phenomenon? This line of questioning leads us to one of the most expansive and controversial ideas in all of cosmology, the multiverse hypothesis. Here, our entire cosmos, with all its hundreds of billions of galaxies, is just one single bubble in a vast, frothing cosmic foam. In this staggering vision, the larger reality is a perpetual, seething arena of space-time where new universes are constantly budding off, each with its own Big Bang. Each of these bubble universes could be a separate reality, isolated from all the others, and each might be governed by a completely different set of physical laws. In one universe, gravity might be repulsive. In another, the speed of light could be a slow crawl. The fundamental constants that make our universe capable of hosting life, the precise strength of nuclear forces or the mass of an electron, could be random variables different in every single bubble. This idea emerges naturally from certain interpretations of cosmic inflation, the theory that our universe underwent a period of hyper-fast expansion in its first fleeting moments. If that inflationary energy can decay in some regions and not others, it could create a never-ending cascade of new universes. The controversy, however, is immense. If these other universes are permanently disconnected from our own, forever beyond the horizon of our observation, how can we ever prove they exist? This moves the discussion from the realm of testable science into the domain of philosophy. Are we to accept a theory that, by its very nature, might be untestable? The philosophical implications are equally dizzying. In an infinite multiverse, every possible event must happen somewhere. Every choice you did not make is being lived out in a parallel reality. Every historical outcome that seems miraculous in our world is mundane in another. This can feel either deeply unsettling or profoundly liberating. It challenges our very definition of reality, suggesting that our particular universe is not special or fine-tuned for life, but simply one among an infinite number of random outcomes. We just happen to live in the one where the numbers came out right for us to be here to ponder the question. This idea of separate realities pushes at the very limits of what we consider real, but a more radical proposal suggests that reality itself is an illusion. The holographic principle argues that our seemingly solid, three-dimensional universe might be nothing more than a projection, a hologram encoded on a distant, two-dimensional surface. Think of the experience of watching a movie. The images appear to have depth and volume, with characters moving toward you and away, but all of that information is actually stored on the flat, two-dimensional surface of the screen. The holographic principle suggests our cosmos operates in a similar, though far more complex, way. The information describing every particle, every force, and every event within our three-dimensional world could be entirely encoded on a vast cosmic boundary that surrounds us. In this view, the world we experience is a kind of magnificent translation, a projection from that lower dimensional surface. The physics behind this is not magic but stems from the study of black holes. Scientists discovered that the amount of information, or entropy, a black hole can contain is not proportional to its volume, as you might expect, but to the surface area of its event horizon. This was a profound clue that perhaps the fundamental degrees of freedom of a system reside not within its volume but on its boundary. If this is true for a black hole, could it be true for the entire universe? The idea remains deeply speculative and fiercely divisive. For its proponents, it is an elegant solution to deep problems in theoretical physics, potentially unifying gravity with quantum mechanics. For its critics, it is an untestable abstraction that stretches the definition of science to its breaking point. If true, it means that the solidity of your hand, the vastness of a galaxy, and the flow of time itself are all emergent phenomena, a grand cosmic mirage generated from a reality that is fundamentally simpler and flatter. We are left to wonder if we are not three-dimensional beings at all, but merely complex patterns of information painted onto the edge of the world. The solidity of our reality might be the most convincing illusion of all. A growing number of philosophers and technologists argue that we are not living in a base reality, but inside an incredibly sophisticated simulation, much like a character in a hyper-advanced video game. This is the simulation hypothesis, and its arguments often begin with a simple, logical progression. If an advanced civilization ever develops the computing power to run detailed simulations of its own history or of entire universes, it would likely run not just one but a vast number of them. In that case, the number of simulated minds would drastically outnumber the number of original biological minds. Therefore, if you were a conscious being, the statistical probability is that you would find yourself inside one of the countless simulations, not in the original reality. Philosopher Nick Bostrom formalized this trilemma, suggesting that one of three propositions must be true. Either civilizations always go extinct before reaching this technological capability, or they have the power but choose not to run such simulations, or we are almost certainly living in one. The rapid advancement of our own computing and virtual reality technologies gives this idea a chilling plausibility. We are already creating immersive digital worlds, and it is not a huge leap to imagine a future where those worlds are populated by sentient artificial beings who believe their reality is fundamental. From a scientific perspective, the hypothesis offers potential, if speculative, explanations for some of the deepest quirks of our universe. Why do the fundamental laws of physics appear to be based on mathematical relationships, as if the universe were running on code? Could the strange, pixelated nature of quantum mechanics, where things only become definite when observed, be a kind of processing optimization, a way for the simulation to save on computational resources by only rendering the details that are being looked at? Yet the critiques are fierce and fundamental. Many physicists argue this is not science at all, but a modern form of metaphysics. A theory that cannot be tested, falsified, or observed is by definition outside the bounds of scientific inquiry. How could we possibly design an experiment to detect the programmers? Any evidence we find within the simulation would, by its very nature, be part of the simulation. Proponents sometimes suggest looking for glitches in the fabric of reality, or for fundamental limits like the Planck length, which could act as a built-in resolution limit. But these could just as easily be inherent properties of our base reality, not signs of its artificiality. The debate forces us to confront the very nature of existence and consciousness. If we are in a simulation, does that make our lives, our loves, and our struggles any less real? Or does it simply mean that reality is layered, and our creators might themselves be living in a simulation, in an infinite regress of worlds within worlds? We are left with a haunting question about the nature of our own consciousness. Are we the original players, or are we merely the characters, unaware of the game we are in? Gravity may be the dominant force in our cosmic models, but what if we have been dramatically underestimating the power of electricity? This is the provocative claim at the heart of the plasma universe, also known as the electric universe theory. In this alternative cosmology, the primary architect of the cosmos is not gravity but electromagnetism. It envisions a universe permeated by a sea of plasma, a fourth state of matter where gases are so hot that electrons are stripped from their atoms, creating a swirling, electrically conductive soup. Within this cosmic plasma, vast electric currents can flow, weaving through space and generating powerful magnetic fields over astronomical distances. Proponents argue that these colossal electromagnetic forces are the true sculptors of the universe, responsible for forming and powering galaxies, stars, and even planetary systems. They suggest that the majestic spiral arms of galaxies are not just gravitationally bound structures, but are physical manifestations of immense, rotating Birkeland currents, vast cosmic power lines that carry energy across the void. The Sun, in this view, is not primarily powered by internal nuclear fusion, but by external electric currents flowing in from the galactic circuit, with sunspots and solar flares being electrical phenomena. The theory also offers its own explanations for planetary geology, attributing the features on rocky worlds like Mars not to water and wind, but to catastrophic electrical scarring from planetary-scale lightning discharges in the ancient past. This entire framework stands in stark opposition to the standard model of cosmology, which places gravity firmly in the driver's seat, with electromagnetism playing a secondary, localized role. The mainstream astrophysical community's rejection of the electric universe is nearly universal and intensely firm. The primary criticism is a profound lack of evidence. The theory makes specific, testable predictions about the electrical properties of space and the behavior of celestial bodies that have consistently failed to materialize under rigorous observation. For instance, to sustain the immense currents it proposes, space would need to be far more electrically conductive than our measurements show, and the model's alternative explanation for the cosmic microwave background does not match its precise blackbody spectrum. Mainstream scientists argue that while plasma physics and electromagnetic effects are undeniably important in specific contexts, like the solar wind or nebulae, elevating them to the dominant cosmic force ignores the overwhelming success of gravitational theory in explaining the large-scale structure and evolution of the universe, from the orbits of planets to the lensing of light by galaxies. Clusters, the debate is more than a simple scientific disagreement. It is a fundamental clash of paradigms pitting the established, mathematically rigorous edifice of general relativity and the Big Bang against a more intuitive, visually dramatic, but scientifically unsubstantiated challenger. It forces us to ask a difficult question: are we clinging to an incomplete picture of the cosmos, or is this alternative a compelling story that simply does not align with the universe as we observe it? The debate over cosmic origins inevitably collides with one of humanity's oldest and most profound questions, the possibility of a creator. Creationism and its more modern counterpart, intelligent design, argue that the universe and life within it show clear signs of being the product of a purposeful, divine intelligence rather than blind physical processes. Proponents point to what they see as irreducible complexity in biological systems, arguing that certain molecular machines are so intricate that removing any single part would cause the entire system to fail, making a gradual, step-by-step evolutionary origin impossible. They also point to the fine-tuning of the universe's physical constants, the precise numerical values that govern the strength of forces like gravity and the nuclear interactions. If any of these constants were even slightly different, they argue, atoms would not hold together, stars could not form, and life would be impossible. This perfect balance, they suggest, is powerful evidence for a designer who set the initial conditions with a specific goal in mind. The scientific community, however, draws a firm line. Its methodology is built upon methodological naturalism. the principle that scientific explanations must rely solely on natural causes and testable phenomena without invoking the supernatural. From this perspective, intelligent design is not considered a scientific theory because its core premise, an unobservable and untestable designer, lies outside the bounds of scientific inquiry. Critics argue that what appears to be irreducible complexity often is not, with scientific research continually uncovering plausible evolutionary pathways for complex structures. Similarly, the apparent fine-tuning of the universe might be explained by other concepts such as the multiverse, where a vast array of universes exist with different constants, and we simply inhabit one of the rare ones where conditions are right. This is not merely a debate about data, but a fundamental conflict over the very definition of knowledge and how we come to know what is true. Can science, by its own rules, ever address the question of a creator? Or are we looking at two different, non-overlapping ways of understanding reality, one based on empirical evidence and the other on faith and philosophical reasoning? This enduring controversy forces us to confront the limits of our tools for understanding and asks whether the cosmos is ultimately a closed system of cause and effect, or an open book with a signature on its first page. Perhaps the ultimate cosmic collision was not between stars or galaxies, but between entire realities. The Ekpyrotic universe theory proposes exactly this, a model where our universe was forged in a violent encounter between two immense, multidimensional membranes known as brains. This idea emerges from the depths of string theory, which suggests the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. For the mathematics of string theory to work, it requires more than the three spatial dimensions we experience. It posits the existence of extra, hidden dimensions, all curled up at a scale far too small for us to perceive. In this framework, our entire three-dimensional universe could be a brain, a kind of island or sheet existing within a higher dimensional space called the bulk. The theory paints a breathtaking picture. For eons, another brain, a parallel universe, floated silently in this bulk, separated from our own by a minuscule gap. Then, drawn together by an unknown force, these two colossal membranes moved toward each other. They did not collide and shatter, but instead passed through one another. The energy of that cataclysmic encounter, a gentle brush in the grand higher dimensional scheme, was funneled directly into our three-dimensional brain. This immense infusion of energy became the hot, dense state we now identify as the Big Bang. In this view, the Big Bang was not the beginning of space and time, but merely a dramatic moment of heating and expansion within a pre-existing reality. The appeal of the Ekpyrotic model is its elegant resolution of several cosmological puzzles. It naturally explains why our universe appears so remarkably uniform on large scales, because the pre-collision brains were vast, cold, and smooth, and the collision itself imparted that uniformity to the newborn cosmos. Yet this very strength is also the theory's greatest weakness, the profound challenge of finding any observable evidence. The collision happened in a higher dimensional reality, and all the direct evidence for it would be locked away in those inaccessible dimensions. Scientists have searched for a specific signature the model predicts in the cosmic microwave background, a pattern of gravitational waves from that primordial event. So far, no such signal has been detected. Without a tangible, testable prediction that can be confirmed, the Ekpyrotic universe remains a beautiful and mathematically compelling story, a ghost from another dimension whose existence we can only infer but may never prove. The idea of a cosmic cycle finds a new and startling form in the mind of a Nobel laureate. Roger Penrose's conformal cyclic cosmology proposes a universe that does not bounce, but rather transforms, where the end of time in one era becomes the very beginning of time in the next. In this extraordinary vision, our universe is not the first, nor will it be the last. It is simply one eon in an infinite, unending sequence. The theory hinges on a profound symmetry between the universe's fiery birth and its cold, empty future. Billions of years from now, after the last stars have died and the last black holes have evaporated, the cosmos will be an immense, dark, and nearly featureless void. All that will remain is a sparse sea of radiation and fundamental particles stretched across an incomprehensibly vast space. In this state, the universe loses all sense of scale. A single photon would experience the entire cosmos as effectively infinite, just as it did in the first moments of the Big Bang. Penrose's genius was to recognize that these two states, the ultra-dense beginning and the ultra-smooth end, are mathematically identical when you remove the concept of scale altogether. In this conformal geometry, the infinite future of one eon can be seamlessly attached to the singularity of the next. The end of our universe is not a finale, but a bridge. That cold, empty expanse, devoid of any recognizable structure or time, becomes the hot, dense fireball of a new Big Bang, birthing a fresh eon with its own laws, particles, and eventual story of galaxies and life. It is a cycle not of collapse and rebound, but of forgetting and rebirth, where the universe effectively resets by forgetting everything, including its own scale. The controversy around this idea exploded when Penrose and his colleagues claimed to have found evidence. They argued that if one universe truly gave rise to the next, there should be faint imprints, echoes from the previous eon, left on the new one. They turned their attention to the cosmic microwave background, the oldest light in our universe. Their analysis pointed to strange, concentric circles within this radiation, regions where the temperature variations were unusually smooth. They interpreted these circles as the gravitational shock waves of colossal collisions between supermassive black holes in the eon that came before ours. These titanic events, they suggest, left permanent, ghostly bruises on the fabric of our newborn cosmos, visible today as subtle rings in the sky. The scientific community met this claim with intense skepticism. Other teams analyzing the same data argued that these apparent circles are no different from what you would expect to find by random chance in a universe with random fluctuations. The statistical significance of the finding has been fiercely debated, with many cosmologists concluding it is a classic case of seeing patterns in the noise. Yet the idea remains captivating. It offers a poetic and grand vision of eternity, where the universe continually renews itself not through violent collision, but through a quiet, geometric inevitability. It challenges us to see the entire cosmic story not as a single, linear narrative, but as one chapter in an infinite book, where the final page of one story is, quite literally, the blank first page of the next. This fine-tuning of the universe presents a puzzle so profound it has its own name, the Anthropic principle. It is the simple yet staggering observation that the fundamental constants of nature appear to be perfectly calibrated for our existence. The force of gravity, the strength of the nuclear forces, the mass of an electron, if any of these values were altered by even a minuscule fraction, the universe as we know it would not exist. Stars would never have ignited, complex atoms would never have formed, and life would have been an impossibility. This cosmic balancing act feels too perfect to be an accident. For some, this is the most compelling argument for a designer, a cosmic architect who set the dials with intention. How else, they ask, can we explain such impeccable luck? The scientific response to this apparent fine-tuning often points toward the multiverse. In a vast, perhaps infinite ensemble of universes, each with its own random set of physical laws, it is statistically inevitable that at least one universe would have the right combination for life. We should not be surprised to find ourselves in that one, because we could not exist anywhere else. Our very presence as observers selects for the rare universe that allows for observers. The debate then becomes a philosophical standoff. Is the universe telling us it was made for us, or are we simply the lucky winners of an unimaginably vast cosmic lottery? There is no experiment we can run to prove one interpretation over the other. we are left to ponder whether the universe is a product of purpose or a product of probability on a scale so grand it defies comprehension. Our universe seems too perfectly ordered to be a simple accident, yet a strange and unsettling thought experiment born from 19th century physics suggests we are not just unlikely, we are statistically impossible. This is the paradox of the Boltzmann brain. It begins with the second law of thermodynamics, which states that the universe as a whole is sliding from order into disorder, a state known as entropy. In a completely random and chaotic system, fluctuations can occur. A random jostling of atoms could, by sheer chance, assemble a fully formed, self-aware brain, complete with false memories of an entire life it never lived. According to pure probability in an eternal, chaotic universe, such a brief, isolated flicker of consciousness would be vastly more likely to spontaneously form than an entire, stable, 13.8 billion-year-old cosmos with galaxies, planets, and a continuous history. The odds of a single brain popping into existence for a moment are astronomically bad, but the odds of our vast, ordered universe are infinitely worse. So the paradox hits with full force. If we trust the laws of probability, it is far more probable that you are a lone Boltzmann brain, having just randomly assembled in the void with a complete but fictitious memory of reading this sentence, than that you are a real person in a real, ancient universe. This is not a theory about what actually happened, but a devastating logical argument that exposes a flaw in our cosmological thinking. It challenges the foundations of how we apply probability to the cosmos. If our best models of an eternal or inflationary multiverse inevitably lead to the conclusion that disembodied brains should outnumber ordinary observers like us, then those models might be deeply, fundamentally wrong. The paradox forces physicists to seek cosmologies that naturally avoid this bizarre outcome, pushing our understanding of the universe's origin toward theories where such random, brain-sized fluctuations are not the norm. It is a ghost in the machine of modern cosmology, a whisper from the void that our entire reality might be the most improbable thing of all. The unsettling logic of the Boltzmann brain forces us to question the very stability of our cosmos, but another theory offers a different kind of container for reality. Our entire universe might be the interior of a colossal black hole. This is the provocative claim of Black Hole Cosmology. In this model, the Big Bang was not an explosion in a void, but the violent birth of a singularity from within a parent black hole belonging to a larger meta-universe. The event horizon of that parent black hole would then form the ultimate boundary of our own cosmos, the point beyond which we can never see or communicate. The mathematics can be eerily suggestive. The equations describing the expansion of our universe and the geometry around a black hole's event horizon bear a striking, and some argue compelling, resemblance. Furthermore, the estimated density of the universe at the moment of the Big Bang is curiously similar to the density of matter crushed into a black hole singularity. It is as if our entire cosmic history is simply the evolution of a black hole's interior from its initial, infinitely dense state to its current vast expanse. The theory then takes a truly mind-bending turn. If our universe exists inside a black hole, then every black hole that forms within our own cosmos could itself be the seed of a new baby universe, spawning an infinite fractal of realities. A star collapses in our sky, forming a point of infinite density and birthing a new space-time continuum entirely separate from our own, a cosmos with its own physical laws and potentially its own stars, galaxies, and life. This creates a stunning picture of a cosmic lineage, a great tree of universes where each black hole is a branch point to a new reality. Yet for all its conceptual elegance, this idea faces a mountain of evidential hurdles. The most significant problem is one of fundamental isolation. By their very definition, black holes are one-way doors. Nothing, not even information, can escape from behind the event horizon. If we are inside such an object, we are permanently cut off from the parent universe. We could never receive any signal or evidence from that external reality, nor could we ever hope to observe the other baby universes being born from our own black holes. The theory, in its pure form, becomes fundamentally untestable, a beautiful story that might be true but can never be verified by any experiment or observation we can conceive. This places it in a difficult position within the scientific method. How do we distinguish a theory that is truly profound from one that is merely an unfalsifiable fantasy? The debate forces us to confront the limits of our knowledge and the tantalizing possibility that the ultimate nature of existence might be forever hidden from us, locked away behind an event horizon we call the sky. Our everyday experience tells us time flows in one direction, an unstoppable river from the past into the future. But what if this is a grand illusion? The theory of a time-symmetric universe proposes that the fundamental laws of physics do not actually distinguish between past and future. At its heart, this idea suggests that the Big Bang and a potential Big Crunch are not two separate events, but are in fact the very same moment in time. Imagine the entire history of the cosmos not as a straight line, but as a single, immense loop. From our perspective, we are hurtling away from the hot, dense Big Bang. Yet from the perspective of the far future, if the universe were to collapse, everything would be rushing toward the ultra-dense Big Crunch. The time-symmetric view argues these two perspectives are physically identical. The beginning is the end, and the end is the beginning, fused into one. This immediately shatters our most basic intuition about cause and effect. How can the effect, the final state of the universe, also be the cause of its own beginning? The theory forces us to consider that causality itself might not be a fundamental rule of the cosmos, but merely an emergent property, a pattern that arises from our limited point of view within the cosmic loop. The greatest challenge to this idea comes from the second law of thermodynamics, the undeniable observation that entropy or disorder always increases. We see an egg shatter, but we never see it spontaneously reassemble. This gives time its apparent arrow. A time-symmetric universe seems to demand that entropy would have to decrease on the other side of the cosmic loop, leading toward the Big Crunch. This would mean that for half of cosmic history, cause would precede effect, and for the other half, effect would precede cause. Such a reality is utterly incompatible with our conscious experience, where memory only works in one direction and we feel we can influence the future but not the past. Are we simply living in the half of the loop where entropy is increasing, completely unaware of the other, reversed time half? Or is our perception of time's flow an inescapable part of being a conscious observer within a universe that is, at its most fundamental level, perfectly symmetrical? This theory does not just challenge our models of the cosmos, it challenges the very nature of our own consciousness and its place within the ultimate structure of reality. Before the cosmos was found to be expanding, it was widely believed to be a permanent, unchanging fixture. The idea of a static universe is one of humanity's oldest cosmic models, a vision of a realm that was simply and eternally there, with no beginning and no end. In this timeless picture, the stars were fixed to a celestial sphere, and the overall arrangement of the heavens was constant and everlasting. It was a philosophically comforting view, suggesting a stable, ordered cosmos that required no explanation for its origin because it had always existed. This perspective held sway for centuries, deeply embedded in both scientific and cultural thought. The universe was not a story with a first chapter, but a perpetual, silent presence. This all began to unravel in the 1920s when an astronomer named Edwin Hubble made a series of meticulous observations that would shatter this ancient paradigm. By measuring the light from distant nebulae, which we now know are entire galaxies, Hubble noticed something peculiar. The light from almost all of them was shifted toward the red end of the spectrum. This redshift was not a random finding, it followed a clear pattern. The farther away a galaxy was, the greater its light was redshifted. The most straightforward interpretation of this discovery was that these galaxies are all rushing away from us and from each other. The entire fabric of space itself was stretching, carrying the galaxies along with it. The universe was not static at all. It was dynamic, evolving, and had a history that began with a bang. Hubble's evidence was so compelling that the static universe model was effectively abandoned by mainstream science, seen as a beautiful but definitively disproven idea. Yet, in the decades since, a few voices have attempted to revive a form of the static universe, though with significant modern twists. One such proposal suggests that the redshift of light might not be caused by the expansion of space, but by some other, unknown physical process. Perhaps light gradually loses energy over its immense journey across the cosmos, causing its wavelength to stretch and appear redder. This tired light hypothesis, as it is called, could theoretically produce a redshift without requiring any cosmic expansion. The problem is that this idea struggles to explain other key pieces of evidence, most notably the precise pattern of the cosmic microwave background and the observed abundance of light elements. The evidence for an expanding universe is woven together from multiple, independent threads, and no single alternative explanation has managed to account for all of them at once. The static universe, in its classic form, remains a relic of a bygone cosmological era. Its modern revivals serve as an important reminder that even our most established theories must constantly face scrutiny. They challenge us to ask whether we have interpreted Hubble's landmark discovery correctly, or if we are missing a deeper, more subtle truth about the nature of the cosmos. John Wheeler pushed the anthropic principle into truly uncharted territory. He asked a question that still echoes through physics. What if the universe requires conscious observers not just to perceive it, but to actually bring it into being? This is the participatory anthropic principle, a concept that shatters the traditional role of an observer as a passive witness. In Wheeler's mind, we are not just living in a universe fine-tuned for life. We are active participants in its very creation, reaching back across time to solidify its past. The most famous illustration of this is his delayed choice thought experiment. Imagine a single particle of light, a photon, traveling from a distant quasar, passing on either side of a massive galaxy that acts as a gravitational lens. It journeys for billions of years. Before it finally arrives at our detector here on Earth, it has been behaving as a wave, taking all possible paths simultaneously. Now we set up our equipment. If we place a screen to catch the photon, it will behave like a particle and strike one specific point. But if we instead use a device with mirrors to detect which path it took, it will reveal its wave like nature. Our choice of measurement, made now, in the present, seems to determine what that photon was doing for billions of years in the past. Did it travel as a wave or a particle? The answer depends entirely on how we choose to look at it today. Wheeler took this quantum weirdness and scaled it up to the entire cosmos. He suggested that the universe only came into a definite state when it finally produced conscious beings who could look back and observe its history. All the potentialities of the past, all the possible ways particles could have interacted in the early universe, remained in a fuzzy, undefined state of probability until the first conscious mind observed a consequence of those ancient events. In this view, we are not just reading the story of the universe, we are writing it, and the ink is only drying as we turn the pages. The controversy this ignites is immediate and profound. It seems to place human consciousness, or any consciousness, at the very center of cosmic causality, a notion that many physicists dismiss as a modern form of anthropocentrism. They argue that the universe got along just fine for billions of years before any life appeared, and that the quantum effects Wheeler describes do not require a conscious observer, just a physical interaction that leaves a record. Yet the idea persists, haunting the intersection of quantum theory and cosmology. It forces us to confront the deepest mystery of all, the relationship between reality and our awareness of it. Are we truly the authors of cosmic history, or are we merely its most attentive readers? Perhaps the most foundational aspects of our reality are not what they seem. Space and time themselves might be secondary phenomena, illusions that emerge from a far more basic and unfamiliar reality. This is the theory of the emergent universe. It proposes that the dimensions we move through and the time we experience are not the bedrock of existence, but rather collective behaviors, much like the concept of temperature is not a fundamental property of a single atom. You cannot point to one atom and ask for its temperature. Temperature is an emergent property, a statistic that only has meaning when you consider the collective, chaotic motion of trillions of atoms. In the same way, the smooth, continuous fabric of space-time described by Einstein might be a large-scale average of something else entirely, a seething, chaotic quantum substrate we cannot yet perceive. At the tiniest possible scales, at the so-called Planck length, our classical understanding of geometry may break down completely. Instead of a smooth continuum, space might be composed of discrete, quantized grains, a cosmic pixelation. Time might not flow uniformly, but advance in tiny, indivisible ticks. The ongoing quest is to discover the fundamental entities from which space and time are built. Is it a network of spinning loops, as in loop quantum gravity, a constellation of interacting quantum bits or qubits, or perhaps a vast collection of entangled particles whose interconnections literally weave the fabric of space itself? The mathematics behind these ideas is extraordinarily complex, but the core concept is a profound shift in perspective. We are not living within a pre-existing stage. The stage itself is being built moment by moment by the underlying interactions of a more primitive reality. The actors are creating the theater as they perform. This research is on the bleeding edge of theoretical physics, and with that frontier comes intense skepticism. The primary challenge is a familiar one: testability. How do you design an experiment to detect the granularity of space-time when the predicted scale is a trillion times smaller than an atom? Any particle accelerator we could possibly build would be far too weak to probe such minute distances. Scientists are searching for indirect evidence, such as subtle variations in the speed of very high-energy light particles traveling across the universe. If space is truly grainy, then different colors of light might navigate its microscopic texture at slightly different speeds. So far, no such effect has been conclusively observed. For critics, this lack of empirical grounding is a major weakness. They argue that without a clear path to experimental verification, the idea of emergent space-time remains in the realm of mathematical speculation, a fascinating story that may or may not correspond to physical reality. Yet the pursuit continues, driven by the powerful intuition that our deepest theories of gravity and the quantum world will never be reconciled until we understand what the universe is really made of, one level deeper than space and time themselves. Another path through the endless cycle of cosmic rebirth avoids the crunch entirely. The Steinhardt-Turok model presents a breathtakingly elegant version of the cyclic universe, one where the grand reset is not a collapse, but a collision in a higher dimensional realm. In this framework, our three-dimensional universe is a brain, a vast membrane floating in a higher dimensional bulk, forever dancing with a parallel brain just a tiny distance away. These two worlds are drawn together over trillions of years by an invisible force, eventually smashing into each other, but this is not a destructive crash. The collision is elastic, a cosmic bounce that transfers immense kinetic energy into each brain. This sudden, violent infusion of energy is what we perceive as the Big Bang, a period of intense heating and expansion that sets off a new cosmic cycle. After the collision, the brains fly apart, and the new universe begins to cool and expand, forming galaxies and stars. Dark energy then takes over, driving a long period of accelerated expansion that eventually stretches the universe into a vast, cold, and empty state. perfectly preparing it for the next slow approach and inevitable collision. The cycle has no beginning and no end, an eternal, rhythmic dance. A key strength of this model is its elegant solution to the problem of entropy. In a traditional Big Bang to Big Crunch cycle, entropy would be expected to increase with each cycle, making subsequent universes more and more disordered. The Steinhardt-Turok model cleverly sidesteps this. The long, dark energy-driven expansion phase before each collision dilutes the universe so thoroughly that it effectively resets the entropy counter. The cosmos becomes smooth, flat, and empty, wiping the slate clean for the next collision to begin a new, low-entropy era. This gives the theory a significant advantage over older cyclic ideas, as it provides a natural mechanism for avoiding a thermodynamic dead end. Yet this beautiful picture is not without its own profound challenges. The theory relies on the existence of extra dimensions and specific properties of the brains that are, as of now, completely hypothetical. The most significant criticism is the same one that haunts many grand unified theories: a lack of testable predictions. While the model suggests a specific pattern of gravitational waves from the primordial collisions, these signals are predicted to be incredibly faint, far below our current ability to detect. Furthermore, the precise physics of the brain collision itself remains a subject of intense debate, with some physicists arguing that the process would be unstable or would not produce a universe that looks anything like our own. When compared to Roger Penrose's conformal cyclic cosmology, the contrast is stark. Penrose's model is a cycle of transformation and forgetting, where the universe loses all structure and scale before rebirth. The Steinhardt-Turok model is a cycle of collision and kinetic energy, a more direct and mechanical process. One seeks to explain fine-tuning through an infinite series of resets, while the other embeds our cosmos in a deeper, hidden dimensional landscape. Both offer a vision of eternity, but they ask us to place our faith in entirely different kinds of unseen realities. The choice between them is not just about equations, but about which version of an endless cosmos feels more fundamentally true. What if the smooth fabric of space-time is an illusion, a kind of cosmic mirage? Causal set theory proposes exactly this, arguing that the true foundation of reality is not a continuous expanse but a vast collection of discrete, indivisible points. Think of the universe not as a flowing river but as a colossal, shimmering cloud of dust motes. Each mote is a fundamental event, a single grain of space-time itself. These grains are not scattered randomly, however. They are connected in a specific web of relationships, a network of cause and effect. One event, one grain, can influence another only if it lies in its past. This structure, a vast collection of points with a strict order of causality, is the causal set. It is the universe at its most fundamental, a digital blueprint from which our experience of a smooth, four-dimensional reality emerges. The central challenge for this theory, and the source of its greatest controversy, is the leap from this sparse, grainy network to the seamless continuum we all experience. How does a collection of discrete points conspire to create the smooth curvature of space described by Einstein's general relativity? Proponents argue that just as a television screen uses tiny, discrete pixels to create a seamless image, the sheer density of these space-time atoms creates the appearance of continuity. If the grains are fine enough, our measurements are too coarse to detect the underlying pixelation. The mathematics suggests that from the simple, causal relationships between these points, the familiar properties of space and time, its geometry, and even its dimensionality can be derived. It is a profound idea that the flow of time and the vastness of space are not primitive, but collective phenomena emerging from a deeper, more primitive structure of pure causality. Yet the leap from this elegant mathematics to our observable world is immense. Can this abstract web of cause and effect truly account for the dynamic, warping fabric of space-time around a planet or a black hole? Critics point out that while the theory beautifully captures the causal order of events, it struggles to naturally reproduce the full, rich geometry of Einstein's universe. The path from a causal set to the specific equations of general relativity is not yet clear, and some physicists wonder if the theory is too minimal, if it has stripped away so much that it cannot rebuild the complexity we see. The debate hinges on this very question of emergence. Are we living in a reality that is, at its heart, a vast and intricate chain of causes, a cosmic story written in points and connections? Or is the smooth, continuous stage of space-time the true foundation, with its apparent graininess merely a mathematical artifact? This theory pushes us to consider that the most fundamental law of the cosmos might not be about forces or fields, but about the simple, unbreakable logic of what causes what. Our own arrow of time might be pointing in only one possible direction. A truly symmetrical universe could require its perfect opposite, a mirror world born in the same instant as our own. This is the mirror universe theory, a speculative idea suggesting the Big Bang did not create one cosmos but a pair. In this mirrored reality, time flows backward from our perspective. A cup of coffee there would spontaneously warm up, assembling itself from spilled droplets that leap back into the mug. People would grow younger, remembering the future instead of the past. This is not mere science fiction, but a consequence of a fundamental symmetry in physics known as CPT. CPT stands for charge, parity, and time. The laws of physics are believed to be almost perfectly symmetric if you simultaneously reverse the charge of every particle, turn the universe in a mirror, and reverse the direction of time. If you take any particle interaction and perform this triple transformation, you should get another valid interaction. Our universe is filled with matter, not antimatter, which breaks a part of this symmetry. But the full CPT symmetry might still hold if there is another universe that is our perfect CPT mirror. In that world, everything would be made of antimatter, it would be spatially mirrored left to right, and crucially, time would run backward. The Big Bang would then be a single, symmetric event that gave rise to these two twin universes, one evolving forward in time and the other evolving backward. The profound challenge, of course, is one of connection. How could we ever interact with or even observe a universe where time is reversed? Any signal we tried to send would, from their perspective, be arriving from their future and would be encoded in the physics of antimatter. It is a cosmic conversation where every message is hopelessly scrambled by the fundamental rules of causality. We are left with a haunting possibility that for every action we take here, an equal and opposite action is unfolding in reverse there, a perfect cosmic balance forever hidden from our view. The singularity at the start of time represents a fundamental failure of our known physics. But what if that point of infinite density was never actually real? This is the promise of quantum gravity, a field of physics seeking to merge Einstein's theory of gravity with the bizarre rules of the quantum world. Its various approaches all suggest that the Big Bang was not a true beginning, but a transition from a prior cosmic phase. One of the most compelling visions comes from loop quantum cosmology. In this model, the fabric of space-time is not a smooth continuum, but is woven from a network of tiny, indivisible loops. These loops act like a fabric with a finite, incredibly small weave, preventing matter and energy from being crushed into an infinitely dense point. As you rewind the expansion of our universe, gravity does indeed become overwhelmingly powerful, squeezing everything together. But just as the collapse seems destined to create a singularity, the quantum nature of space itself pushes back. The loops of the space-time fabric resist further compression with a ferocious repulsive force. This resistance causes the collapsing universe to bounce back like a cosmic rubber ball. What we call the Big Bang was in fact this moment of rebound, the big bounce from a previous universe that had contracted down to a tiny but finite size. This elegant idea naturally removes the troubling singularity, replacing a moment of nothingness with a bridge to a past cosmos. But loop quantum cosmology is not the only contender in the quest for quantum gravity, and the debate over the correct path is fierce. String theory, for instance, describes the Big Bang not as a bounce but as a collision of branes in higher dimensions. Another approach, called causal dynamical triangulations, builds space-time from tiny, geometric building blocks that change shape over time. Each of these frameworks offers a different mathematical language to describe the universe's birth, and each makes different, testable predictions. For example, loop quantum cosmology predicts a specific, subtle pattern in the cosmic microwave background, a faint imprint left by that primordial bounce. So far, our telescopes have not detected this signature, but the search continues. The central controversy lies in which approach is most viable. String theory is mathematically profound but requires unobservable extra dimensions. Loop quantum gravity is more minimalist but struggles to fully incorporate other forces like electromagnetism. The choice between them is not just about equations, it is a philosophical divide over the very nature of reality. Is the universe composed of tiny, vibrating strings, or is it a network of interwoven loops? The answer to what happened before the Big Bang might depend entirely on which quantum path we take, a decision that remains one of the most important and unresolved in all of modern science. Every black hole might contain a secret exit. If the immense gravity of a black hole represents a one-way door from which nothing can return, then a white hole is its theoretical opposite, a cosmic exit from which nothing can enter. It is a region of space-time that violently and continuously expels matter and energy, a fountain of cosmic material erupting into reality. While a black hole's event horizon is a point of no return for anything falling in, a white hole's horizon would be a boundary that nothing from the outside could ever cross. It would be a source, not a sink. This leads to a breathtaking, if wildly speculative, possibility. What if the colossal explosion we call the Big Bang was not the birth of a universe from a singularity, but the spectacular eruption of a white hole? In this hypothesis, our entire cosmos could be the interior of a white hole that began spewing its contents nearly 14 billion years ago. The initial state of infinite density and temperature would be the moment this white hole switched on, pouring forth all the energy that would eventually coalesce into every galaxy, star, and planet we see today. The appeal of this idea is its elegant symmetry, connecting the two most violent events in physics, the birth of a universe and the death of a star in a black hole, into a single, continuous process. Yet this remains one of the most controversial and purely theoretical ideas in all of cosmology. The first and greatest problem is that white holes are fantastically unstable according to our current understanding of general relativity. A white hole would be an immense source of energy in an otherwise empty space, and anything with mass or energy falling onto it would instantly disrupt its delicate structure, causing it to collapse back into a black hole. For a white hole to last long enough to create an entire universe, it would have to exist in perfect, pristine isolation, a condition that seems almost impossible to achieve. Furthermore, we have absolutely no observational evidence that white holes exist. No telescope has ever detected a violent, unexplained fountain of energy that matches the theoretical description. The hypothesis also faces a profound causality problem. If our universe is the interior of a white hole, then what exists on the outside? The mathematics suggests it would be a separate region of space-time, a parent universe where the white hole resides. But this leads to an infinite regress where every universe is just a white hole inside a black hole from a previous cosmos. While this creates a poetic vision of a great cosmic chain, it does not answer the ultimate question of origins, it merely pushes it back one step further. We are left to wonder if the Big Bang was truly the first moment, or if it was simply a local event, a single white hole flowering in a much vaster and older meta-universe we can never hope to see. Our search for cosmic simplicity reveals a hidden world of perfect symmetry. The theory of supersymmetry proposes that every fundamental particle we know has a hidden, superpowered twin. For every electron, there should be a heavier partner called a selectron. For every quark, a squark. This elegant doubling of the particle roster is not just for aesthetic appeal, it is a potential key to unlocking the universe's deepest secrets. In the frantic energy of the first moments after the Big Bang, these superpartners would not have been hidden at all. They would have been abundant, interacting freely with their standard counterparts and fundamentally shaping the evolution of the infant cosmos. This supersymmetric state would have been a period of perfect balance, a cosmic harmony that resolved some of the most vexing problems in physics. For instance, it could naturally explain the existence of the mysterious dark matter that holds galaxies together, as the lightest of these superpartners could be the very particle that forms this invisible cosmic scaffolding. It also provides an elegant solution to the hierarchy problem, the puzzling question of why the force of gravity is so unimaginably weaker than the other fundamental forces. Supersymmetry smooths out the violent quantum fluctuations that would otherwise make this disparity nonsensical. Yet for all its mathematical beauty and explanatory power, this theory is mired in a deepening crisis. The controversy is stark and undeniable. We have never found a single one of these superpartners. The world's most powerful particle accelerator, the Large Hadron Collider, has been searching for a definitive signature of supersymmetry for years. It has crushed particles together with unprecedented energy, recreating conditions not seen since the universe's first trillionth of a second. So far, it has found nothing but silence where new physics was expected to roar into existence. This absence is profoundly troubling. The simplest and most elegant versions of supersymmetry predicted these particles should have shown up at energy levels we have already probed. Their non-appearance forces theorists into a corner, compelling them to devise increasingly baroque and contrived versions of the theory to explain why the superpartners remain just out of reach. This leads to a difficult question: is supersymmetry a beautiful idea that is simply wrong, or is nature just more complex and subtle than we hoped? The dream of a perfectly symmetrical cosmos endures, but it is a dream waiting for a reality to prove it true. Even the most elegant cosmic bounce needs a physical mechanism, something to push back against the crushing weight of gravitational collapse. This search for a tangible cause leads us to a universe built not from point-like particles, but from the very fabric of reality itself. The bouncing cosmology from string gas proposes that the universe is fundamentally composed of a dense, hot gas of vibrating strings. These are not ordinary strings, but the one-dimensional loops and filaments postulated by string theory, the entities from which all particles and forces are thought to arise. In this model, the entire cosmic story is driven by the behavior of this primordial stringy soup. As the universe contracts, this gas of strings becomes hotter and more agitated. But unlike point particles, which can be squeezed infinitely close together, strings have a unique property. They have a minimum possible size. When the universe shrinks to a certain critical density, the strings cannot be compressed any further. They begin to push back against the collapse with a tremendous repulsive force generated by their own vibrational energy and interactions. This resistance halts the contraction and initiates a powerful rebound, a big bounce that launches a new phase of expansion. The violent, hot beginning we call the Big Bang is simply the moment of this cosmic turnaround, a transition from a previous contracting phase into our current expanding one. This offers a beautifully natural way to avoid the dreaded singularity, replacing a point of infinite density with a smooth, quantum bounce governed by the well-defined physics of strings. The appeal is clear. It provides a concrete, physical picture of a cyclic universe rooted in a leading theory of quantum gravity. However, the standing of this idea within the broader string theory community is one of cautious interest rather than widespread adoption. The model is elegant, but it makes several specific assumptions about the nature of the string gas and the geometry of the extra dimensions string theory requires. Critics point out that for the bounce to work as described, the strings must behave in a very specific way, and it is not yet clear if this behavior is robust across the vast landscape of possible string theory solutions. Furthermore, the theory competes with other cosmological models derived from string theory, such as the Ekpyrotic universe with its colliding branes. Each of these frameworks tells a different story about the moments before expansion began, and there is no consensus on which, if any, is correct. The greatest challenge remains the same one that faces all of string theory: the profound difficulty of finding testable predictions. Can the vibrations of a string gas in the primordial universe leave a unique fingerprint on the cosmic microwave background, a pattern distinct from that of cosmic inflation or a quantum loop bounce? So far, such a definitive signature has remained elusive, leaving this compelling vision of a string-driven cosmic rebound in a realm of beautiful yet unproven possibility. Our final theory pushes the very concept of a beginning to its absolute limit, arguing that the universe did not emerge from anything at all. The null universe hypothesis proposes that everything we see around us, from the most distant galaxy to the very fabric of space and time, originated from a pure and perfect nothingness through a spontaneous quantum fluctuation. This is not a fluctuation in a pre-existing void, but a genesis from a state that lacks space, time, energy, and matter. The philosophical battle over this idea is immediate and fierce, centering entirely on the definition of nothing. Is it even possible for there to be a state of true nothing? And if so, how could anything possibly come from it? Proponents argue that the nothing they refer to is not merely an empty box. It is the complete and total absence of anything, not even a vacuum or a void, which are themselves considered physical constructs with properties and potentials. They turn to the strange rules of quantum mechanics for a possible mechanism. In the quantum world, particles pop in and out of existence all the time, borrowing energy from the vacuum for fleeting moments. If this can happen on a subatomic scale, the argument goes, could the entire universe have simply popped into being on a cosmic scale? The laws of quantum physics, which allow for such uncertainty and spontaneity, might be the only prerequisite, needing no physical container to operate within. This line of reasoning suggests that the universe is, in its entirety, the ultimate free lunch, a fluctuation that simply happened with no prior cause and no need for a creator. Yet the criticisms are profound. Many physicists and philosophers argue that this idea is a semantic trick, a clever relabeling of the problem rather than a solution. If the laws of quantum mechanics are required for the universe to emerge, then those laws themselves are not nothing. They are a form of something, a pre-existing mathematical structure or potentiality. True absolute nothing would have no laws, no potential, and no capacity for change. It would be a state of non-existence so complete that the concept of an event, like a fluctuation, becomes logically impossible. The debate forces us to confront the very limits of human language and logic. Can our minds, which evolved to understand cause and effect within a pre-existing reality, ever truly comprehend a beginning without any prior conditions? The null universe hypothesis stands as the most radical and minimalist in point of our search, a theory that either explains everything by explaining nothing at all, or reveals that the ultimate question of origin might lie forever beyond the boundary of scientific inquiry. 25 possibilities now lie before you, a spectrum of cosmic genesis stretching from the fiery singularity of the Big Bang to the silent emergence from absolute nothingness. We have navigated the strange loops of cyclic time, peered into the holographic surface of reality, and questioned whether we are living in a simulation or the interior of a black hole. Each theory, from the mathematically rigorous to the philosophically daring, represents a profound human effort to answer the oldest question of all. This journey reveals that the search for our ultimate origin is not a closed book but a living, breathing frontier of science. It is the friction of these competing ideas, the relentless clash of data and imagination, that propels our understanding forward, forcing us to constantly re-evaluate our place in the grand scheme. The controversy itself is the engine of discovery, so we turn this final question over to you. After exploring these 25 windows into creation, which one resonates most deeply? Which vision of the universe's birth feels the most compelling, the most elegant, or the most terrifyingly beautiful? Share your favorite theory in the comments below, and if you enjoyed this journey to the edge of cosmology, be sure to subscribe for more deep dives into the mysteries of the cosmos.